Hi, I am Dr. Muhammad Amjad. Uh, I am with you with the second lecture of discrete structures. The previous lecture summary here I will share with you. We were discussed about the introduction of the course, propositions, logical convectives, truth tables, compound propositions, English translation English to logic and logic to English. These are the things which we have discussed already in the previous lecture, lecture 1. Today's lectures we will discuss about the logical equivalences, De Morgan's laws, tautologies and contradictions. Tautologies and contradictions were also discussed yesterday in the previous lecture, but not in details. Here we will discuss them in details. Laws of logic, conditional propositions, these all things will be discussed in these lectures. Logical equivalence. First of all, we define logical equivalent. Logical equivalent is the two propositions form are called logically equivalent if and only if they have identical truth values, which were discussed in a table. For each possible substitution or propositions for their proposition variable, the logical equivalence of proposition forms P and Q is written P equivalent to Q. This will be you can also read read in statistics, any statistical course. So the equivalence is always written in this form. Equivalence of two compound properties P and Q. Here there are three steps we discuss about these three steps. Construct the truth table for P. First of all, we construct the truth table for P and then construct the truth table for Q using the same proposition variable for identical component proposition. And next, check each combination of truth values of the proposition variables to see whether the truth value of P is the same as the truth value of Q. If they are same, then you can say they are equivalent. Equivalence check. This is very simple to check the equivalence between two propositions. If in each row the truth value of P is the same as the truth value of Q, then P and Q are logically equivalent. So simple, so easy. You can check both the values P as well as Q. If both values are the same, then P and Q are logically equivalent. Mean to say, by word you can easily understand. And in the second step, if in some row P has a different truth value from Q, then P and Q are not logically equivalent. If they have different values, truth values, so you can see that they are not logically equivalent. So this is the equivalence check. For example, you can, for example, we say that negation and negation of P, negation of P is equivalent to P. So simple. We make a truth table for P and negation P. If P have a values true, false, then negation P, you already discussed, it will be false and true. Then negation and negation P, negation of P, if this is false, then negation of this value will be true. If this will be true, the negation of this will be false. As you can see, the corresponding truth values of P and negation of P are seen, hence equivalence of negation of P is equal to this. So negation of P is equivalent to P. And in another example, we can show that the proposition forms negation of P and Q and negation of P and negation Q are not logically equivalent. So we construct a truth table for both P. These are the values for Q already discussed in the previous lecture. For negation P, this is P, so this for negation P, and for negation Q we use this column is the values of negation Q. P and Q you can study about this. So these have the values true, false, 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 because only in this row both are true, so this value will be true, otherwise these are false. We discussed in previous lecture. Negation of P and Q, the negation of this column, so this true will become false, this will false, this false will become true, true and true. Now the negation of P and negation of Q, this is the, we have to show the equivalence of these two. Okay, so negation of P and negation of Q, and between these two, so this will be false, false, false and true, because both are true. So we can see that these values are not same. Here is true, here is false, here is true and here is false. So these two columns, these two values, these two propositions are not logically equivalent. For equivalence, these columns should be same. Now we will discuss about the De Morgan's laws. De Morgan's laws state that the negation of an and proposition is logically equivalent to the or proposition in which each component is negated. Please read the statement carefully. The negation of an and proposition is logically equivalent to the or proposition in which each component is negated. The negation of an or proposition is logically equivalent to the and proposition in which each component is negated. These are the statements of De Morgan's laws. Symbolically, De Morgan laws are written in this form. Negation of P and Q is equivalent to negation of P or negation of Q. Negation of P or Q is equivalent to negation of P and negation of Q. These are the symbolically representations of the De Morgan's laws. Now we can ask the question that negate the following compound propositions. John is 6 feet tall. This is the application of the De Morgan's law. John is 6 feet tall and he weighs at least 200 pounds. The bus was late or Tom's watch was slow. This is, to find the solution of these two examples. John is not 6 feet tall, or he weighs less than 200 pounds. And in the second, you can say the bus was not late and Tom's watch was not slow. Inequalities and De Morgan's law. In this, uh, we use by using De Morgan's laws to write the negation of minus 1 greater than x, which is less or equal to 4. The given proposition is equivalent to minus 1 is less than x and x is less or equal to 4. By using De Morgan's laws, we can write the negation minus 1 is greater or equal to x, or we can say that x greater than 4. So we use these inequalities by using De Morgan's laws. Now, tautology and contradictions. We have already discussed the definition of tautology, but not in briefly. A tautology is a proposition form that is always true regardless of the truth values of the individual propositions substituted for its proposition variables. A proposition whose form is a tautology is called a tautological proposition. Definition of contradiction. A contradiction is a proposition form that is always false regardless of the truth values of the individual propositions substituted for its propositions variables. A proposition whose form is a contradiction is called a contradictory proposition. These are the examples. Should the proposition form P or negation P is a tautology and the proposition form P and negation P is a contradiction. So this table is for P, true, false, negation P, false, true. P or negation P, P or negation P, true, true. P and negation P, false, false. So it is a tautology and it is a contradiction. So this is another exercise, you can solve it. Laws of the logic. First law is commutative law, which we have discussed also in the real numbers. Commutative laws, P and Q equivalent to Q and P. That is, P or Q is also equivalent to Q and P. Commutative law also holds in real numbers. Commutative law does not hold in matrices in journal. Associative law. P and Q and R is equivalent to P and Q and R, or you can say in OR, P or Q or R equivalent to P or Q or R. This is OR. Distributive laws. P and Q or R is equivalent to P and Q or P and R. Similarly, P or Q and R is equivalent to P and Q and P or R. Identity laws. P and T tautology is equivalent to P. Similarly, P or contradiction C is equivalent to P. Negation laws. P or negation P is equivalent to T. P and negation P is equivalent to C. Double negation laws, we have already proved this. Negation of P is equivalent to P. Idempotent law, the last one, P and P equivalent to P, P or P is equivalent to P. This is called the idempotent laws. Universal bound laws. P or T is equivalent to a tautology T. Similarly, P and C is equivalent to C. Absorption laws. P and P or Q is equivalent to P, P or P and Q is equivalent to P. Negation of T and C, tautology and contradiction. Negation of tautology is equivalent to contradiction, which is very important law, and negation of contradiction, C, is equivalent to tautology. This is the exercise using laws of logic. Show that we have to show negation of P and Q, and P or Q is equivalent to P. We have by using laws of logic, we have to prove this. We take the left hand side, this one, it will be equivalent to negation of P or negation of Q and P or Q. We use De Morgan's laws. Now negation and negation P, it's equivalent to P, or negation Q and P or Q. We have discussed this by double negative laws, and by distributive law we can combine these two, P or negation Q and Q. P or Q and negation Q, by using the commutative law we can write it as, so by the negation law, this will, we can write it as P or C. So by the identity law we can write this as a P. So we prove this is equivalent to P. Skill in simplifying proposition forms is useful in constructing logical efficient computer and is designing digital circuits. So it's very useful in designing digital circuits and logically for efficient computers. Now the today's lecture summary is logical equivalence, equivalence check, tautologies, contradictions, laws of logic, simplification of compound P. This is the total summary which we have discussed now. Now another examples for this. Prove that negation of this is equivalent to negation of this. R or Q and negation R implies negation P equivalent to this. So we take right hand side and we use different laws, logical laws on this side, and we will make it to the right hand side. First of all we use De Morgan's laws, then we get this negation of R and negation of Q and negation R implies negation P. Now we can use conditional, so we can rewritten as disjunction, negation of R and negation of Q and negation of R or negation of P. Now by double negation this will become R and the remaining will same. Again by using De Morgan's laws we can get this one, negation of R and negation of Q or negation of R or negation of P. Now by using the distributive laws we can write this into this form, negation of R and negation of Q, or negation of R and negation of R and P. By using associative law on this we can write this will be the same, and this term can be written as negation of R and negation of R and negation of and P. This can be written, distributive law, associative law is used in this step. Now this is idempotent law, you use idempotent law, so this will become negation of R and P. Now again, using distributive law on this step, we find negation of R and negation of Q or P. So by using distributive law on this step, we get this one, and in this second last we use commutative law, so this will be the right hand side. You can see that it's very important. You have to remember all the logical laws. Conditional propositions. If P and Q are propositions, the conditional of Q by P is if P then Q, or P implies Q, and is denoted by P implies Q. It is false when P is true and Q is false, otherwise it is true. We have already discussed in the previous section. For example, if you work hard, then you will succeed, obviously. If Sarah lives in Islamabad, then she lives in Pakistan, obviously, because Islamabad is in Pakistan. Implication, if then. This is the binary operator, and this one is the symbol used for this, and this is the truth table, which we already discussed in the previous lecture. These are the values for P and these are the values for Q. Then P implies Q have the values. If both values are true, then the resulting is true, or both have false, then resulting as false. If one of them is true or false, then the result will be false. Interpreting conditional statements. Now we interpret the conditional statements. For example, the online user is sent a notification of a link error if the network link is down. The statement is equivalent to, we can say, if the network link is down, then the online user is sent a notification of a link error. So we can write it. If we're using P, the network link is down. Q, the online user is sent a notification of a link error. The statement becomes Q if P. The online user is sent a notification of a link error if the network link is down. So P implies Q. Another example, when you study the theory, you understand the material. The statement is equivalent to using if for when. If you study the theory, then you understand the material using, if we use P for you study the theory and Q for you understand the material, then the statements becomes P implies Q when P then Q. If you study the theory, then you understand the material, obviously. And the other example, studying the theory is sufficient for solving the exercise. The statement is equivalent to, if you study the theory, then you can solve the exercise. So in this example, if we use P for you study the theory and Q for you can solve the exercise, so the statement becomes P is sufficient for Q. So we can easily write P implies Q. P implies Q means you study the theory, then if you study the theory, then you can solve the exercise. So it's basically conditional, mean to say, if this will become, if you study the theory, then you can solve the exercise. So it's a conditional statements. In real life, we mostly use these statements. This is the activity for showing. You have to show that P implies Q is equivalent to negation P or Q This shows that a conditional proposition is simple, a proposition form that use a not and an or. Show that now this is a solution for the previous example. This table, this is the value of P, this column is the value for Q, and this one P implies Q. Negation of P or Q, negation of P implies Q. So negation of P implies Q. So this one is P and negation Q. From the above table, it is obvious that the conditional proposition is equivalent to not or proposition, or its negates is not of the form if and then. Negations of some conditionals. Proposition: if my car is in the repair shop, then I can't get the class. If we negate this, my car is in a repair shop and I can get the class. This is the negation of the above proposition. In other example, if we say, if Sarah lives in Athens, then she lives in Greece. Sarah lives in Athens and she doesn't live in Greek. Contrapositive or contraposition. If we discuss about the definition of contraposition or contrapositive, the contrapositive of a conditional proposition of the form if P then Q is if negation Q then negation P. Symbolically, the contrapositive of P implies Q is negation Q implies negation P. Mean to say, you have to interchange the places of P and Q with the negation sign. You have to interchange the values of P and Q with negation sign. A conditional proposition is logically equivalent to its contrapositive. Always a conditional proposition is logically equivalent to its contrapositive. For example, if today is Sunday, then tomorrow is Monday. Contrapositive: if tomorrow is not Monday, then today is not Sunday. Both have the same meaning, but logically you can say this is actually you can say these are the totally logical concepts and logical reasoning is behind in this course. If today is Sunday, then tomorrow is Monday. If tomorrow is not Monday, obviously then today is not Sunday. Okay, so that we use this in programming in different areas, in different applications. Now we discuss about the converse and inverse of the conditional. This is also very important, very much important. Converse and inverse. Suppose a conditional proposition of the form if P then Q is given. The converse is if Q then P. If we give if P then Q, the converse is Q then P, and the inverse is if negation P then negation Q. This is too much logical. You can understand deeply. The converse of this statement if P then Q is if Q then P. The converse is if P then Q, and the inverse is, in inverse we use negations, negation P then negation Q. So simple. you can easily remember that in converse we interchange the places. If P then Q. If this is written as is, in converse we can write if Q implies P. The inverse, in inverse we can write negations with P and negation with Q. So symbolically the converse of P implies Q is Q implies P, which I have written in this place. And inverse of P implies Q is negation of P implies negation of Q. So you can easily understand about the definitions of converse and inverse. In converse we replace the values, we can interchange with together P and Q. If P then Q, in converse we can write if Q then P, and in inverse we use the negation sign. Mean to say, if there is negative P, then we use positive P. If there is positive P, we use negative P or negation P. So it's very critical concept. You can easily understand now. I hope so. Next is the biconditional. The biconditional given proposition variables P and Q, the biconditional of P and Q is P if and only if Q, and is denoted P biconditional Q. It is true if both P and Q have the same truth values, and is false if P and Q have opposite truth values. In other words, the words if and only if are sometimes abbreviated if I double F. We have already discussed in the previous lecture. This computer program is correct if and only if it produces the correct answer for all possible sets of input data. This is the truth table for P biconditional Q. So you can easily understand these values. If these are the values for P and these are the values for Q, so P biconditional Q, we can see that this will be true and this will be true. If both values are false, then this will be true. If both values are true, then this will be true. If one of them is false, then it will be false. So if we make another table, these are the values of P and these are the values for Q. So P implies Q means this will be true because P are true. This will be false because this is false. This will be true because this is true. And this will be true if both are false. And Q implies P. Now we use this column as a first column. We replace it in first column. Q implies P. P if and only if Q. P if and only if Q. So we put all these values which we already find in this table: true, false, false, true. And now we use AND between these two columns. So if this is true, this will true, then this will be true. This is true, this is false, then this will false. And if both are false, then this will false. Both are true, then this will be true. So you can easily understand. Now you can understand about the biconditional, conditional statements, which have discussed in the previous lectures also, and now here in this. Now we discuss about the interpreting necessary and sufficient conditions. This is very much important in programming, especially in artificial intelligence, AI, which is in robotics, also used in robotics, and the world is now working almost very much in this field. If a number is divisible by 10, then it is divisible by 2. Think about this statement. This is this statement. If a number is divisible by 10, then it is divisible by 2. The clause introduced by if, remember, you have to put some pressure, some bold on if a number is divisible by 10, the first line is called the hypothesis. It is what we are given. Is divisible a number? If a number is divisible by 10, is called, this is the hypothesis. It is what we are given, or what we may assume, what we are saying, what we may assume. The clause introduced by then, it is divisible by 2. This is this clause. It is if a number is divisible by 10, then it is divisible by 2. This clause, the clause introduced by then it is divisible by 2, is called the conclusion. The first clause is the hypothesis, and the second is the conclusion. So it is the statement that follows from the hypothesis. So we can easily find the result. If a number is divisible by 10, so it is hypothesis which we presented here, and the conclusion will be it is divisible by 2. So this number will be divisible by 2. When the if then sentence is true, we see that the hypothesis is a sufficient condition for the conclusion. Think about this. This is very much interesting sentence I have written in this. When the if then sentence is true, if and then, first if, then, we say that the hypothesis is a sufficient condition for the conclusion. Thus it is sufficient to know that a number is divisible by 10 in order to conclude that it is divisible by 2. So it's very easy. You can easily you will find that if a number is divisible by 10, then if this will be true, then you can conclude easily that this will be divisible by 2. The conclusion is then called a necessary conditions to hypothesis. For if a number is divisible by 10, then it is necessary that it will be divisible by 2. We have already discussed many theorems in mathematics, especially for these like these sufficient conditions, that if we say that if a number is divisible by 10, then it is divisible by x. In general form, if the number is divisible by x, then it's Well, by why? There are many theorems which you have discussed in your previous classes in mathematics. Now, another example considering the proposition: if John is if John is eligible to vote, then he is at least 18 years old. Much exclusive statement. You can easily understand. If John is eligible to vote, then he is at least 18 years old. You can say if John is 18 years old, then he is eligible to vote. You can also uh, write down this. The truth of the condition John is eligible to vote is sufficient to ensure the truth of the condition John is at least 18 years old, because nobody which has no is CNIC that doesn't uh, eligible to vote. So if here we see that we claim that John is eligible to vote, so we can easily conclude that John is at least 18 years old. In addition, if we make addition in this, the condition John is at least 18 years old, this is the condition, is necessary condition for the condition John is eligible to vote to be true. If John were younger than 18, then is not eligible to vote. In every country, in every democratic parties, you can see that you can vote when you have your own CNIC, your own identification, computerized identification card. So here the statement John is eligible to vote is sufficient to ensure that the truth values for that John is at least 18 years old, so that we can easily conclude that John is at least 18 years. It may be he is greater than 18 years, he will be 20, 22, 23, but at least. So we can easily interpret necessary and sufficient conditions in this example. Let R and S are the two propositions. R is a sufficient condition for S means if R, then S. R is a necessary condition for S means if not R, then not S. Now we generalize it. In the previous examples we discussed, we make them specify to some names, some practically in practical field. Now here we use journal, we make it generalize. R is a sufficient condition for S means if R, then S. R is a necessary condition for S means if not R, then not S. R is necessary and sufficient condition for S means if R, if and only if S. So this is biconditional. So you can easily note the necessary and sufficient conditions for R. R is necessary and sufficient conditions for S. It means R if and only if S. You can write it as R if and only if S. If and only if also written as we have already discussed in the previous slides. It can be written as in this form: if I double F. If. Okay. So I hope so you can easily understand the concepts which I have discussed in this lecture. I make these lectures too much. I try my best to make them much easy for you people, so that you can easily understand all the values, all the definitions, all the concepts of these logical uh, things. Now, in the next lecture, we will discuss about the next features and next about circuits and set theory and tabular form and set builder form, universal sets and sets of numbers. We will discuss, and we will improve our speed in two lectures. I try to uh, clear or clarify all the main concepts, so that in the next lectures we will skip them if we have discussed in the previous lectures, so you can easily understand all the concepts in this course. And next we will discuss about union, intersection, Venn diagrams, and set theory, which you have discussed in your course set theory. Next we will discuss about these. Now here, if we take a lecture summary, today's lecture summary was logical equivalence, equivalence check, tautologies and contradictions, laws of logic, simplification of compound propositions. These are all the topics which I tried to cover in this lecture. In the next, we may improve our speed, and we will discuss about the set theory, the Venn diagram especially, and set identities also. We will discuss about these, and we solve some examples of Venn diagrams in and applications of Venn diagrams. You can easily understand these concepts. Applications of Venn diagrams is also very much important in practical life. Next, we will discuss about the relations, ordered pairs, ordered n tuple, Cartesian product of two sets, which you maybe have discussed in the previous classes, but now in the sense of discrete structures we will discuss about these topics, and you can easily understand, and we try to improve our speed and our uh, number of slides in the next lecture, because these two lectures were initial, and the next maybe we will increase our lecture speed, and hopefully we will try to end this course in 16 lectures, and the uh, other remaining topics, types of relations, etc., will be discussed in the next lectures. So until we will come back, be careful and try to make the summary of these lectures and understand all these concepts which I have discussed in these two lectures. If you have any problem, you can easily ask me about any topic. I will mention any link to you for helping you people, and try to implement all these things in real life problems, like we have discussed already in the previous examples. If a number is divisible by 10, then it will be divisible by 2. So these examples should be taken from your daily life, and you can easily uh, put it into your practical life. And we also gave an example. If John is eligible to vote, then he is at least 18 years old. So it's very simple, and we use commonly these sentences in our daily life. uh, for till the next lecture. uh, Thank you.